Hi everyone, my name is Philip and this here is Charlie the Bear. I'm a PhD at the University of Zurich, so ETH Zurich. And specifically I'm part of the Pulp group and Charlie is our mascot. So we can design things like this. That's like one of our headliner projects is these many-core cluster systems, like for example Okami. And obviously we also produce research papers, so if you are interested you can go and read them. And the big question is now, how can we design something of this size at a university? And as you can see, this isn't even the only design we have. We have more than 60 chips. I think by now it's like 70 or something. And we continuously produce more. And the key to this success, to being able to tape out this many chips, is to leverage open source. So let's start at the beginning. How can we even design a chip? On the left you can see you need some kind of idea, a spark. And on the right we have our goal. We actually want a physical chip in our hands. Now the first thing you usually do is you describe what your chip actually does. This is done with RTL, which can be any language, say for example Verilog, System Verilog, VHDL and so on. And this describes the functionality of your chip. Then you give this description to a tool called the synthesizer, and this will turn the behavioral description, so the describing the function, into a connection of different logic gates. And then you pass this netlist to a backend tool, a place and route tool, and it will turn the logical description of how the different gates are connected into a physical design where the geometry is defined. And then finally, you can take this GDS and send it to a fab, like for example IHP, and sometimes later you get your chip back. Obviously we need some additional data to make this work. So the fab defines some technology, like for example IHP's 130 nanometer technology, and it describes this in a PDK, in a process design kit. From that it can then generate a library of standard cells, and the PDK and the library are both used in the tools you see at the bottom to actually design your chip at the end. And then you quite often also have third-party IPs, so you don't want to design everything yourself because that's annoying, so you go to someone else, like for example Open Hardware Group, and you take some of their designs and integrate it into your design. And obviously, very important, at each step you need to make sure that what you want is actually what you get. And this is done with verification, so simulation, logic equivalence checking, and so on. First, let's look at the RTL. So, as I've said, with Pulp platform, we write quite a lot of RTL. So, for example, we have different cores, we have peripherals, we have interconnects, and we have a whole spectrum of different sizes of actual projects. So, we have from very small single core systems to these cluster-based multi-core systems in the middle, and then the very large systems like for example Okami on the right side. And also we have quite a lot of different accelerators for cryptographic functions, for fast Fourier transform and so on. And everything is open. You can just go on GitHub and clone whatever project you want. You can take the RTL, make it your own. Everything is permissive licensed, so you can also use this and develop a chip you can actually sell. So let's take a look at one of these chips. For example, here is Mr. Wolf in TSMC 40. As part of this chip, we had this power converter IP from Dolphin. And this has quite a few advantages. We can actually get to use professional IPs and that has been pretty well tested and designed by actual professionals. they get to demonstrate that their IP actually works, so they can then point to our chip and say, look, we actually designed something that functions as we expected. And then from that, this was the basis for Greenwave's technology to design their GAP8 and GAP9 microcontrollers. So it is also a win for a startup that can take this as a template and design a product from it. I'll wait a second. So now obviously, does this chip work? It's not very interesting if you just have a piece of silicon. So let's put it to use. Let's put it on a very small drone. It's about this size. It's the main microcontroller on this. And then, that's not very important, it has to perform different tasks. Like for example, obstacle avoidance and navigation, environmental exploration, and also object detection. And all these tasks can run at the same time on this one microcontroller thanks to this cluster approach. And obviously it's on a drone, so it has to be energy efficient, and that's also one of our main themes in our group, is to always design energy efficient systems. So in the last 20 years or so, SoCs have become even continuously more complex. So this very large design on the left is now just this tiny speck in the eye of the Kraken chip on the right side. So what used to be a complete and for the time complex chip is now just a very small part of the entire SoC. You can also see this when people develop RTL, so most of the time you hear about this, about the core, but surrounding the core is a complex system. Here interconnects and caches and so on, and you need peripherals to communicate with external stuff. And then on top of that, you also have the software component so that you can actually run useful applications. And then in our case, we have this whole ecosystem of clusters and accelerators and so on we actually want to use. That's the part we actually want to research. And for that, it generates even more software, more compiler support and so on to actually get this to work. And as I said, usually you aren't interested in building this whole system. You want to research some specific topic, or if you are a company, you have some new innovation in one specific part, and you just need SoC around it to demonstrate that this is actually a good approach, the one you have. And this is exactly where this open source silicon approach shines. Because you can have these SoC templates where you pull together designs from other people, and then you can build whatever you want with it, and you can focus on exactly the thing that you develop. And this approach has also worked with industry. So as you can see here, we work with pretty large companies to actually design test chips for them. And again, this is possible because of this permissive licensing scheme. So it's Apache 2.0. It can be used for commercial stuff as well. And other researchers also continue to use our system exactly for this purpose, so that they have a baseline and then they can develop their own stuff on top of it. And again, there are a few small companies involved in this. So now we have this RTL part covered pretty well, and the next step is to unlock the rest of this design flow so that we can make as much open as possible. The first limiting factor is these third-party IPs, which you might use at any stage. Depending on how this is licensed, you can't use it. So you actually need to find third-party IPs with this permissive license. And that's exactly what you can use our systems for, and also Europractice is trying to build a European system to actually collect these open source IPs, and obviously there are other people involved there, like again, for example, the Open Hardware Group. The next limiting factor is the information we get from the fabs themselves. So the PDK and the standard cell library are usually very closed down, and they are very secretive with this information. So here we need fabs like, for example, IHP or Skywater or GlobalFoundries 180 nanometers process, and we need them to open the technology to actually give us the information we need, and to then design a standard cell library around this information. And the final part are the tools themselves. So here, let's first focus on the synthesis tool. Let's first quickly go through what exactly the synthesis tool does. So the synthesis tool is called YOSIS, by the way. The first step is to elaborate your design. So again, we have a description, a functional description of our design, and we need to turn it into cells and the connection between the cells. Here, YOSIS first converts into a high-level representation of the entire thing, where it uses entire arithmetic operations as cells, and then it can perform optimizations on this stage. Then, in a next step, it can convert this high-level representation into a generic gate representation. So these cells on the right, they are very close to actual standard cells, but they aren't technology dependent. They are just internal cells for YOSIS, so that it can start and actually perform optimizations on a gate level netlist. And then the last step is performed in a included tool called ABC, and here the generic gates are then mapped to actual standard gates used in your technology. And in the same step, it also performs a lot of high performance, like leading edge optimizations on this representation. So YOSIS, the tool itself, it is very clearly structured. It has these passes, which are just different commands that operate on whatever the current representation is, so the high-level generic gate or standard cell. And each pass is implemented more or less in one file in the source code. It has a lot of guides, both for users and also for developers, to show them how they can design their own flows or how they can write their own passes if they want to. And it has quite a few regular contributors from the company managing YOSIS itself, YOSIS HQ, and also other stakeholders, people that actually use the tools, have developers that work exclusively on YOSIS. And for you, the main takeaway should be that in less than a week, if you have some experience with C++, you can learn how this tool works, how the data structures work, and you can actually contribute a meaningful improvement. Either improve some paths or write your own. So now we have the synthesis part covered. Now we actually have this netlist, the connection of the different standard cells. And the next tool is the place and route tool. Here we use a tool called OpenRoad. And the first step in it is to actually define a floor plan. So we need to tell it, this is how big our chip should be. Here on the outside, we want our path, so we can actually connect it to the real world. And we have some macros. Here are SRAMs, and we actually need to place them somewhere on our chip. Then the next step, it's not how that's supposed to be. The next step is to plan our power distribution. So we we tell it like the positive power L should be here, the negative power L should be here. So you connect the macros like this and so on. And next, we actually place all these standard cells from the netlist on our chip. And this is done in two steps. The first one just places them roughly, clusters them together a bit, and then the second step does the detailed placement, so it actually searches for a legal position for the cell to be and puts it there. Then next we actually need to generate a clock tree so that all our registers and so on are clocked. This is a separate task because it's pretty complex routing. And then you get something like the diagram on the right side, yeah, like these spreading clock trees. And as a last step, we actually need to route the design. So we actually need to connect all the standard cells with metals. And this is again done in two parts. The first part just plans roughly where the wire should go, and then the second one makes this wire real and start to fix any violations that might occur. OpenRoad started as a collection of different research tools that are put together into a common flow. So for example, the global placer was the research tool Replace, the router was FastRoute, and the clock tree generator was Triton CTS. Then they built this open database data structure, which was designed by industry professionals, and they started to integrate all these research tools into one common flow so that users can actually use them fairly easily. And they also built a lot of supporting infrastructure around it, like for example the GUI, a command line interface, different reporting methods. It can collect different metrics internally and act on them and so on. And it also has a plugin system, so people can extend the GUI and so fairly easily. And again, as you can see, there is a lot more involved to this than just designing the algorithms. If you are somewhat proficient with C++, you can actually go in and help improve the GUI or the command line interface or something else. So now we have the backend tool, place and route as well. The last thing is verification. There are a lot of different tools involved in here, and I don't have time to go into all of them. So I just picked my favorite, which is Verilator. It is a Verilog simulation tool. And now, as you can see, we actually have everything so that we can go to our goal and actually tape out real open source chips. And this is currently what we are able to produce. This is a chip called Basilisk. It was taped out in IHP's 130 nanometer technology. It is fairly large for this technology, 6 by 5 millimeters roughly. It is not very fast, but that wasn't really the goal. The goal was just to see if we can actually design something like this. It has more than 1 million gate equivalent. Actually, it has more than, I think, 500,000 cells by now. It is a lot more than this 1 million put there. And it has a Linux-capable system on it. So you should be able to take this chip and boot Linux. So as you can see, the open source EDA tools can actually already handle pretty complex designs. So if you remember the one of the graphics at the beginning, these single core simple systems we have covered. The next step are bigger systems like these cluster systems and so on. So again, Basilisk is, to my knowledge, the first end-to-end open source Linux-capable SoC. It has a DRAM interface and other peripherals as well. It has a silicon-proven RTL, so we expect this to work. And it is fairly large for open source EDA tools. And during the development of this, we also found quite a few problems in this open source flow, and we started to improve them. So we started with this blue dot at the top right, and towards the lower left is direction of better, so smaller and faster. And we actually went quite a bit, and we are still not where the commercial tools are at the moment, but we are closing this gap. It is getting smaller every day. And this as well, you can just go to GitHub and run it yourself, but be aware you need a fairly powerful computer to design this chip. So the benefits of open source are clear to me, and I hope they are also clear to you. It enables easier collaboration between researchers because you are not limited by non-disclosure agreements from the fabs. Other researchers can actually reproduce your results ideally perfectly, so they can check that you have actually done your homework. And then the next thing is the industry also profits. For example, for security applications, this transparent chain of trust so that every step is auditable is important, and it also lowers the initial costs, so startups don't have to spend millions of dollars just to get the tools. And this can also accelerate the speed at which you can develop new things and release new products. And then the last step is education. With this increased accessibility to the tools and without any black boxes, you can check at each step what the tool does. You can actually also enable people to learn how these tools work internally. And you can get people to experiment with the flow and the algorithms used in the EDA tools. So education is actually already gaining quite a bit of momentum, like for example this eFabless chip ignite flow, or also the tiny tape-out flow, where for a few $100s you can have one of these very small cells in there and actually have your own small design on a real chip in the end. And on the very right side you can see tiny tape-out also already works on IHP's technology, and it should be available within a year or so on IHP as well. And on our side, we have developed this CROC SoC, which is meant to be a very simple chip for students. So on the left side, you can see there are just the minimum number of things you actually need to get a somewhat functional system. And on the right side, you can see it on a 2 by 2 millimeter chip, so it's not very large. And here the goal was that it was as simple to understand as possible. So everything is just in one repository, no annoying dependencies and so on. And soon there will also be guides on how to use this. We have students currently working on that. It is designed to be as flexible as possible, so that if you are interested in using this, you can go in and modify whatever part you want. For example, if you want to include your own core, then you can just exchange the core and use your own design. And every step of the flow is exposed, and we are getting there with the documentation. That always takes a bit of time. And the last thing is that it is easy to run. It runs on older laptops. It uses less than 4 GB of RAM peak. It runs in a Docker container, so it should work on every operating system. And the main flow is completed with just 4 make commands and I think about 8 script files behind it. And we will actually use this for our VLSI 2 lectures starting next year. And the idea is that each year we take about 4 to 5 student designs and then actually produce them with IHB. So our conclusion is that we use open source because it just works. It allows us to manage complex designs and actually produce very complex chips. It facilitates this industry-academia relationship, which is important because at the end of the day, we want that our students can then go and work in the industry and learn real things. It creates auditable designs, and you can reproduce our results perfectly. And it can also enable research into new directions because we generate data that was previously not available to researchers. And very important for us is that open source sees no borders. There is no European and Chinese and American open source, and attempts to stop this exchange are stupid and don't make sense. There can, however, be different support for these things. So maybe one country wants to invest more money in it than others. So open source is global, and it can just have more or less support in each country. But we shouldn't lock down anything. No problem. And obviously, there is still more to come. We have just started using these open source EDA tools. My PhD is on this subject, so for the next 4 to 5 years, we will continue to push the front of what you can actually design with these chips, with these tools. That's everything.
Before the Q&A, I just want to resonate with your remarks that open source sees no boundaries, because, you know, being hosting this kind of tracks for 4 years, it's always been that, oh, we're American open source, we're Chinese open source, stuff like that. But open source is borderless. It's just like, I don't know why people are so bonded to this kind of boxes and put themselves into this kind of regulations. Yeah, it's just so sad.
I think the important part there is that we are not politicians. We don't need to play these games.
Yes, exactly. And we use open source because it works. I'm a software engineer, but the first time that we can do this kind of things is back in 2019, because eFabless is giving a talk to the RISC-V Summit, and it all sparks me to get involved in this kind of thing. So open source works. Yeah. Okay, let's get the Q&A. Is there any questions? Really? No? Okay. Yeah.
So may I ask, where did you get those macro like SRAM or the other macros you use?
So the SRAMs we currently use are on IHPs on the PDK. They are part of it. So there are already a few SRAMs available, and there should be more incoming soon.
See, thank you.
Thank you. One remark from my side. On our GitHub, we have several SRAM sizes available. If you need a certain size, please ask us, then we can check. It might be possible to generate it. Yeah? Okay, thank you.
Any more questions?
Okay.
And are there any 101 course for the open source IC design in your mind?
On the topic of courses, so this Croc chip, this one, we are planning to make like a wiki or something where you can actually go through our whole course. So actually go through designing the RTL and also learning how the backend works with step-by-step instructions, exercises, and so on. We are currently working on that. I think it will take about a year or so until that's actually public.
I see. You really want to ask more questions, or? Okay. I want to resonate with this question because many of us come from the Department of Computer Science or Electronic Engineering, so we know how to do this. But that's for the open source. Like when the first time I learned how to program is like in my elementary school, and I randomly ran into a book and read it whole through and start programming since then. But for learning how to do the digital design or do the ASIC things, it's more or less more complicated. And the Professor Chen from Kinmen is actually asking this question for his students because somehow you don't just have the right materials to ignite this learning path. It's very slopey. The learning curve, yeah, is very steep. Yeah, so that's a problem for all of us. And if Crux works, then I really hope to learn more about it. Yeah.
And also on this point, we're already in talks with people from other countries to then either translate our course or the EU, a few EU European universities are working on a similar project, and our goal is that more or less the same exercises and same explanations are available in different languages. So it is actually as easy for students to learn as possible.
I see. Thanks a lot. Any more questions?
So I see in your chip list, all the chips you make, you use the commercial tool, and right now you use the open source tools. So do you have a small comparison between these two flows, and how the outcome difference?
So comparisons to the commercial tools are always a bit difficult because they don't like it. And you don't want to anger them. So here, that's also the reason why you just have this cloud for the commercial tools. The commercial tool is somewhere in there. They are fine with like these rough comparisons, but they usually don't like if you actually publish comparative results, and also with respect to the flows, to the commands and so on, they can be quite restrictive on them. So we can't really say more than we are getting there.
By the way, that because for the eFabless and the Skywater, they have the the template SoC called Caravelle, and so is Croc also in this kind of manner that there will be your user design area and the harness SoC? Is this kind of the same architecture you're using?
So that's actually one thing we want to come to do different than Caravelle. So this is Caravelle for everyone. You have this user design area where you can put your own design, but then the pad frame, so where the pads are and a bit of assistance infrastructure is given. So you can't design the whole chip however you want. And the goal with Croc is that we just have this minimal infrastructure and pins on the left here, and they are given, you can change them, but everything else you can change. You can change the size of this chip, you can change what exactly is in there, you can change the core if you want to, whatever you want. So we want to be as flexible as possible.
Thanks for the explanation. Is there any more questions? Okay, if not, then give a big applause to the speaker.